Right. All right, so today my plan is to give you guys a quiz. And even though I'm not grading it, you should still treat it like a quiz, right? So we're gonna go the same period of time I would have given you for a quiz. You should probably like consider this to be quiz conditions, so don't try to pull from any of the material. This is a way of you assessing yourselves and how you're doing in the class so far. The questions here come from 11.3 and 11.4. You should try to write complete solutions. When I'm finished with it, when you're finished with it, I'm gonna let you hold on to the quizzes, and I'm gonna go through how I would solve the questions, why I made the choices that I made, and then you should use these as a study guide. I'll post it. This is also posted on the Canvas page as a blank, so you can refer to it back later, okay? And then after that, if there are homework, so for those of you online, it's up on the Canvas page, you should be able to follow along on the same timeline. I trust you to be honest with yourself. And then after that, I've got a nice lineup of questions from 11.1 and 11.5 that we can work together. We can work in groups or individually on solving some questions where I just throw you a pile of series and ask questions, and you got to figure out which method to use. It's harder than it sounds. All right, so 1, 2, 3. So when you get this, you might as well get started. Like I said, I am not going to pick it up, but I will provide solutions when we're done. Put those back. To 15 past 1, actually going back to the back of this row. 1, 2, 3. 1, 2, 3. All right, so this is going to run. Did everybody get one? That's the first thing. Have we got one? All right, so go ahead and get started. We're going to do this for 10 or 15. Yep. We're going to do this for 10 or 15 minutes, depending on how I see everybody doing, and then I'll call it and we'll go through the solution. So get started. You two guys on the computer. All right, so maybe you guys like 2 more minutes to finish up.
That was aggressive. I'm sorry.
All right, let's talk about these. Let's do the finish. Get that through. I'm going to talk for a moment to people who maybe struggled with these questions or they're looking at them and they didn't know what to do on one or both of them. So the nice thing about these quizzes, remember, the point of these quizzes is not intended to make you feel bad if you didn't understand how to do the questions. It's to give you a little simulation of what this is going to feel like on the exam in here, right? There's going to be there's going to be 5 or 6 of these. And mastering, knowing which pattern means which test is going to be what leads to success on this stuff. And it's not as hard as it seems to do that. So let's actually go through the solutions. Quite a number of people finished these. I did not snoop around to see who was doing it correctly or not, but let's actually let us walk through them. You guys can tell me what to do. Okay, so the first question was sum from n equals 1 to infinity of 5 plus 2 root n over 3n squared plus n minus 6. Now, the way I think about these questions is I think of the menu of options that I have when I'm looking at a problem to solve it. I'm being asked to check for convergence, right? So the first thing I think here is, all right, what can I actually do? What have we learned? Even if you go section by section, 11.1 was about sequences. Well, it's not a sequence. 11.2 was about the definition of series, which included geometric and telescoping. And even if you didn't know that the quiz was about 11.3 and 11.4, you'd know that this isn't a geometric series, right? It's not something to the n over something to the n. 11.3 is about the integral test. 11.4 is about the comparison test. This is the topics of this quiz, are integral and comparison. And then finally, in 11.5, in our set so far, we have the alternating series test. And yes, this probably feels a little bit like calculus 2, where there's a million types of integral. And you have to figure out on the basis of what a problem looks like, what kind of integral it is. So because it's a quiz from 11.3 and 11.2, you know this is either integral or comparison, or one of the comparison tests. So the first question you have to ask yourself is that a function you would ever want to integrate? The answer is, hell no, I'm not going to integrate that. There's roots and like rationals and partial fractions might have to be involved, but they can't be because there's a square root of n. So I'm actually going to think about doing this with the comparison test. And not just the comparison test. I think it would be most productive to look at this thing with the limit comparison test. Now, why would I choose that? Why limit comparison over comparison? It's a choice that you make when you're setting a question up. Does anybody have anybody who picked limit comparison? Why? Yeah. Okay. So what does this look like when n gets big? What series does this end up looking like? So as n goes to infinity, the terms here look like what? Well, on the top, yeah, it's definitely a p series because on the top you get 2 root n because that's the dominant term of the numerator. And the dominant term of the denominator is 3n squared. Now, remembering that root n is n to the 1/2, that tells you that this thing kind of looks like 2/3 of 1 over n to the 3/2. The 2/3 doesn't even matter, right? Multiplying a series by something doesn't tell you if it converges or not. It might matter if you were doing a comparison test as opposed to a limit comparison, but this is what this series ends up looking like when n gets big. And if you said, the problem is, if you wrote down 5 plus 2 root n over 3n squared plus n minus 6, I have no idea if that's bigger or smaller. None. I mean, and I don't want to do a bunch of algebra to figure it out. Right? I mean, over here I've got this, and maybe that's bigger, but I don't want to do this. Too much work. And it just might be false. Might be a false statement. So instead, what we're going to do is we're going to use the limit comparison test, because when I write down a comparison, when I find something to compare to and I don't get an obvious inequality, I should use the limit comparison test instead. So the limit comparison test says that I'm supposed to take the limit as n goes to infinity, one of the series, over the other one. That's the thing I've chosen to compare to, because as n went to infinity, this is how I find my comparison. I look at the dominant terms. Okay, so doing that gets you, I mean, there's multiple ways to do this question in terms of constructing the limits. So just because you didn't get the same comparison as me doesn't mean your answer is wrong. 3 n to the 3/2 over 2, 5 plus n to the 1/2 over 3n squared plus n minus 6 when you multiply that out,
The two,
I forget something.
the two, the end. Like the square, the end of the 1/2. the side of the-
Oh, there's a 2 here. Yeah. Okay, so 15 n to the 3/2 plus 6n squared over 6n squared minus 12. Those are the dominant terms in this limit, right? Remember, you're allowed to use the ideas from calculus 1 and pre-calculus when you compute limits. The leading term on the top is 6n squared. The leading term on bottom is 6n squared. This limit is 1. So how do we conclude? Well, 0 is less than 1, which is less than infinity. So the series converges by the limit comparison test. Okay. So you should suspect when you see a structure like this. I mean, so if you're looking for clues about what indicates what method, if you have fractions that involve things that look like polynomials, I mean, it's not really a polynomial because there's an end to the 1/2 up here, right? But if you see fractions in your series that look like a polynomial-ish thing divided by another polynomial-ish thing, you should suspect that the comparison or limit comparison tests are in play. Okay. Yep.
Why can't you just write it like as a case series and then because perhaps it will have to stay with one.
What do you mean write it like a
Like,
series?
or because the thing that you is.
Okay, so but when you do that, okay, so I was actually gonna have people score what they did here. I'm gonna give you like different score versions of this. So what you're saying is, so you're giving the sort of, the way that a math professor would talk about this would be the non-rigorous version of the argument, because this is the proof that what you said is true. Your argument is this series is basically this series. That's the argument you just made, right? And that this is a convergent P series. So if this was a 5-point quiz and you did that, which is totally correct. This idea is exactly correct because that's just what we did right here, right? You made the argument about why it converged, but you didn't invoke the theory. Remember, we're learning this the first time, right? So you found the comparison, but you didn't tell me why the fact this comparison exists forces the series to converge. Once you're out of this class, absolutely you could look at that and say, clearly it converges. It's like 1 over n to the 3/2, right? But for this class, because this is the first time you learned it, if you made this argument, I would give this a 3 out of 5. It's got all the intuitive core of the problem inside of it, but not the rigorous part at the end. If you got all the way down here, if you found the comparison but didn't show that it converged, that's like a 2. If you wrote literally anything on this problem, it's a 1. Right? So you can score yourself if you want. Literally anything. If you wrote down an inequality and used the comparison test, even though you were wrong, that's still a 3. So if you use this inequality, even though you didn't know it was true, that's still worth a 3. If you got to this point and didn't know how to compute the limit, that's worth a 4. Okay? That's the way I would approach this, because the way I think about the grades for these problems is 0 is basically like you didn't do anything, you left it blank, don't do that. 1 is you tried literally anything other than writing the problem down again. 2 is you knew something about how to proceed. 3 is an answer that is essentially correct or intuitive but doesn't do all the details. 4 is you missed one key step. 5 is right. Okay. Any other questions on this one? So yes, obviously, like if you were talking to me in person, you said, "Does this?" And I said, "This converge." You say, "Yeah," because it's like a P series with 3/2. I would say, "Yes, of course." Questions about this one? Okay, let's look at the other one. And the other one is literally a homework problem. This is question 2. By the process of elimination, because this one was from a comparison test, the other one must be the integral test, right? And you know, on an exam, the way that I'll just tell you up front that my theory of writing exams is I like to test different ideas in each question. So if you get a pile of series, you know that like you're not going to have 2 with the integral test in them. It's going to be 1, right? I have a limited amount of real estate on the page. You have a limited amount of time. 1 idea per question. So you can go, oh my God, where's the integral? Go find it. Okay. So second question. N equals to infinity 1 over n times the natural log of n to the 5th. Now, even if you didn't know by the theory of math classes, this must be an integral test, why would you suspect it's an integral test anyway? It's just screaming at you. There's a u substitution here, right? If u is equal to the natural log of n, then du would be 1 over n. And there's a 1 over n right there. Okay. To do the integral test, I have to check 3 conditions. That is part, no. That, chewing on this one. So that's actually, that's part of the getting the points on this. So if you just integrated this thing and didn't do the condition checking, that's a 3. You did the test, but you didn't show that it applied, okay? So I'm going to show a function f of x, which is 1 over x times the natural log of x to the 5th. I will tell you the easiest possible way to get to make this problem shorter and get 4 points too. 1, f is positive. You can just put it. I mean, what is there to check? Of course it's positive, right? X is, we're only considering values of x bigger than or equal to 2. So yes, of course it's positive. The amount of work I'm writing down here is the amount of work you have to do. 2, f is continuous. Well, the only bad spot is that x is equal to 0, and 1, right? X is equal to x. So x is equal to 0 and x is equal to 1 are bad. But we're looking at x bigger than or equal to 2. So we're cool. That's okay. All right, now, what's the sort of triage time-saving thing you could do on this question if you're an exam? You're really trying to smoke out time at the end and maximize your points. If you really don't want to compute the derivative to show this function is decreasing, it might be worth taking the docked point and just assert that f is decreasing. You're not going to get full points unless you compute the derivative and argue to me the function is decreasing. But as long as you write f is decreasing, here, people try to sneak this one past me. F is decreasing because f prime of x is negative eventually. Now that is a beautiful piece of mathematical BS right there, because it means you know what to do, you just didn't want to spend the time to do it. Yep. You know the denominator is decreasing?
I mean,
Do you know the denominator is an increasing function? Are you going to tell me why? No. So even an intuitive argument will work here, but you still have to justify what you say. Yes, x times the natural log of x to the 5th is increasing because x is an increasing function, and the log of x is an increasing function, and the log of the 5th power is an increasing function. So everything on the bottom is increasing, which means that this whole thing must be decreasing, right? If you want to say that, you're welcome to. Okay? I'm not sure that saves you much time over just writing down the derivative. But like if you say this with no justification at all, you're going to lose a point. Even if you get the rest of the problem right. Yep.
You say that like n1 over, like if you substitute n plus 1.
Yes. Yes, absolutely. You could do this with the ends as well, except this is a function of a continuous variable x, not a function on the integers, right? What if it does some squiggly thing in between the integers? Then the integral test wouldn't apply, right? So I guess my answer was yes. Oh wait, I mean no, right? That you can't, for a problem like this, the function has to be decreasing as a function of a real variable, not a function of an integer. So checking n and n plus 1 and those inequalities against each other is not enough because it doesn't tell me what happens in between the integers.
So for like integral tests,
For the integral test, you basically have to use the derivative or some kind of argument about the fact that the denominator is increasing. Okay. So if you wanted full, here we use, like Sydney's argument would be this: x times the natural log of x to the fifth increases. So 1 over x natural log of x to the fifth increases. Even that probably is enough if it's obvious that this is an increasing function. If it's not, then you're still trying to BS me. That I appreciate. I like it when students know enough about how this game works to try to set it up to pretend that they did math. At least you've told me you know what to do, right? You've identified the obstacle to the question when you do that, which is why this is okay. The core of it, though, is once you know that you can apply the integral test, whether you do it with a derivative or whether you do it with an argument like this, is you actually have to do the integral. And the entire justification for using the integral test was that you saw a u substitution. I mean, if you're going to use the integral test, you have to be able to integrate the thing. Now, nobody that is a mature calculus 3 student would ever try to compute a Riemann integral with infinity as the limit of integration. That would be a sin. Because that doesn't exist. This is not a thing. It's just shorthand for this. I'm in a long-term fight. Some of my engineering colleagues who are totally happy to slap infinity around like this number. But it's not. It'll get you in trouble in a lot of cases, which is why I insist. So if you actually compute this, I think you get, after u equals the log of x, you should get something like log 2 log t 1 over u to the 5th du. After you do the substitution, after you take the integral and you compute the limit, I believe this entire thing turns into 1 over 4 times the natural log of t, no, not t, of 2 to the 4th. This integral spits that out after you compute the limit. So now there's some work here. To go from here to here is a step I'm allowed to do on the board because I'm not trying to log a dead horse. But you know, this step right here involves taking antiderivative, plugging in the limits of integration, and evaluating this limit. But it's going to be 1 over log t to the 4th, which is 0. So this step is a step you should check you know how to do. Now, what does it mean? I got a number out. So what? What are the conditions on a number that comes out of the integral test? Just finite. That's all there is. This is finite, and so therefore, thus series converges by the integral test. Now you might wonder why I insist that you tell me what test you used when it's obvious that you just took an integral of something. And the answer is some of the math that I get in this class sometimes when people submit it, I can't actually tell what test you use. Because there might be 3 different tests written down, and you have to tell me which one is the one that you're actually using to conclude the answer. Okay, so even if you think it's totally clear, make sure that you tell me which test that you use. Okay. Now, I will say these are standard sorts of examples. This is exam level difficulty. This isn't too easy for an exam. And it's not too hard for an exam. This is an exam level question. So you should expect to see questions like this, basically exactly like this. Again, series of polynomial type things, series where there's an obvious u substitution that falls out, you should expect to see that. Okay. Are there questions about this one or steps I could add if I've left out that you would like to see? Okay, so how would you score yourself on this one? Well, as soon as you said integral test, you earned yourself a 2. If you tried to integrate anything, no matter what nonsense you did, you got a 2 at least for doing an integral, right? If you check the conditions, that's worth a point, condition checking. Did you know what they were? Did you do everything in the question except prove to me that f is decreasing, then you got a 4. Did you do everything correctly but calculate your integral wrong and get infinity and say it's divergent? You got a 4. If you did everything right, you do one step wrong. Okay, that happens to people, right? They get in here, they get infinity instead of a number because you do some step wrong, you got a 4. Not a 0, 4. Okay? But assuming everything else is good. Okay. This grading scale is supposed to encourage you to try things and show me that you know what the mathematical thought is behind what you're doing. Any other questions on this before I give you a couple things to work on before I let you go? Yep.
So definitively, are you gonna allow us to say stuff like that?
Yes. Yes. Like that?
Yeah.
I absolutely would. This argument right here, I would take.
Okay.
Okay. If I give you a function where it's not obvious that it's decreasing though, like think where there's terms adding and subtracting and fighting each other. I mean, this one is really simple because the numerator of this is constant,
Right.
right? If the numerator and denominator are both functions, then it's more complicated, right? This one is simple enough that I would buy this argument.
Okay.
Right. Unfortunately, it's like a judgment call on your part. But if you get a question like this and you want to know if it's sufficient, like you do that, you just ask me on an exam. That's enough, and I'll tell you. All right. So I guess before I let you guys go for the weekend, I'm going to do a couple more problems here that I'd like to, just like we did on Tuesday. I'm going to write a couple problems up on the board, just 2 or 3. 1 from 11-2. I'm not going to tell you which sections they come from, right? I'm going to give you 1 from 11-2, 1 from 11-3, 1 from 11-4, 1 from 11-5, maybe. It might sound like a lot of questions. And you guys can tell me what that. So again, as before, you're welcome to work together. Those of you online, I will answer these questions in solutions that I post this weekend, like prior. I'm just pulling up in my textbook. I could find some good ones. Chapter 11. All right, here we go. All right, so together or independently, I would like to know the following. Does the question 1. Sum 3n plus 1 4 3n-2 converge or diverge? 2. Let's look at sum a equals 1 to infinity of a e to the minus k squared. We will look at the sum of minus 1 to the n but and 4. Go. 4 series. On your own or together? Feel free to chat, ask me for questions. I would say probably in 13 minutes you have time to work 2. Just pick 2. What's the hardest looking one up there? Do that one. I promise there's 1 each from 11-2, 11-3, 11-4, 11-5 up here. maybe since you guys are so quiet, it would be a good exercise to try to identify which is which before we get started. What is this? I want 4 different answers from 4 different people. What kind of series is this? Why is it geometric?
The constants in the base and then variables in the whole square.
Yeah. In fact, is it gonna converge or diverge, by the way?
With that,
Okay. So geometric. What about this one?
integral.
Okay. So we thought this was geometric. This one is an integral. Why is this integral? Somebody else. Why would you use the integral test on this? An obvious U substitution, right? U is k squared, du would be k. How about this one? This is completely obvious what this is. It must be alternating because it's got that -1 to the end. There's no other thing you're going to use here. So by default, this one is
Oh, that's comparison.
this has to be comparison. I mean, we're by process of elimination, if there's one of each. So this is going to be a comparison test. This is the trickiest one on here probably. So either comparison or limit comparison test. That should guide your thinking over the next 10 minutes. Okay, but the process of identifying which is an important part of this.
Are the only conditions, are that it's continuous and then no limit to zero?
You don't even need continuity. With the alternating series test, it's not continuous, it's decreasing if you want.
Oh, yeah,
So the limit being 0 and decreasing frequently come together, but not always.
yeah. Okay, right there.
When you do that, focus on just trying to like see like, oh, it's positive, like how much do you exploit it, just like.
Well, so like, you actually have to, you just have to do the integral, right? So after you, so like, yeah, okay. If you're trying to say it's positive, unless like there's some complicated function here, all I really need to know is that you look at this and say, well, that's a positive number, and k is positive. This is always positive, so positive times positive is positive. I could literally know more than that, right?
Okay.
It's like, don't belabor that, like showing this thing is positive. It's usually obvious it's positive, and it's more, do you know? It's a way to, the real thing is it's checking to make sure that you don't try to integrate something that looks like this, right? Because it's possible that people do this. They try to integrate stuff where the function is not always positive, and then things go wrong.
And we have to show that these are conditions every time, but are you ever gonna have a question on exams where they don't need to do this?
I mean, for the integral test, you mean specifically?
Yeah.
Yeah, so if I was gonna do that, it would probably be more like it's possible I could ask a true false section, and one of the questions in the true false section would be, can the integral test can be applied to this function, true or false? And then I'm much more likely to have you do that than have people make a mistake and continue all the way. I meant to have everybody stop at step 2 when the function was not decreasing or whatever, continuous, but then instead they went on and did the whole problem because they missed that step. So it wouldn't really be fair to do that. So if I ask you to do the computation, I'm going to give you something that is going to at least pass the conditions for the integral test. But it's also possible I could ask you as a true false question, something like, so that might look like this, true false. The integral test applies to the sum of say cosine. I'm trying to make a function that wobbles and gets smaller. So how about cosine squared of n over right? And the answer would be no, because this is not a decrease. The answer would be a decreasing. It's not a decreasing function. It looks like this. So it kind of like wobbles and then wobbles smaller and smaller and smaller because the 1 over n is making it go to 0. So while the wobbling means it's not a decreasing function, something like that, where the point would be it would be obviously not decreasing. I mean, this is probably not a good example because maybe it's a little mysterious, but that's how I would do that. I wouldn't do it in a question. For number 1, number 4. Yeah, dude. Yep. Yeah, so oftentimes the test by divergence cuts off the need to do anything more complicated, because the other way that you would look at this is you would compare it to 3 to the n over 2 to the n, right? And then say, oh, well, 3 to the n over 2 to the n. In limit comparison, that's going to turn out to be 1 to 3 to the n turns over. I mean, limit comparison tests under the conditions of divergence often fail exactly when this thing fails the test for divergence. So you always have the test for divergence available. It's the first thing you should always check. All right, those of you that want to pack up and get out of here, welcome to. But anybody who wants to stick around and work another 5 minutes, I'm not going anywhere. Yep.
Good question. So on number 3, I remember from yesterday is that bn plus 1 is less than bn.
Yep.
But for the start of that function, it's not true.
It's as long, so again, it's an eventual condition. Because in all of these series problems, the issues always happen as you go out to infinity. So as long as it's eventually decreasing, everything is okay.
Okay. You're posting these solutions.
Yes. Yeah, so just like I posted the last one, I'll write these up in the same style and post them up on the Blackboard page. Or Canvas, sorry. All right, so those of you leaving, which is, I presume everybody have a good weekend. Try to make it back to town on Tuesday. Yeah.